Good morning, good evening, good afternoon, everybody. Welcome to today's MLIR Open Design meeting. Today we'll have Alex from Google presenting on index analysis in XLA GPU. Take it away, Alex.
Yep. Hi, everyone. I'm Alex from XLA GPU team at Google. I want to present to you indexing analysis in XLA GPU that was developed, I think, since November 2023, and has a lot of applications within Google. Well, within XLA GPU for now. Indexing map is an affine map plus domain metadata. The affine maps that we have in MLIR, they don't have any context about the variables they operate on. So they don't know the ranges of the variables. They don't know how to simplify some of the expressions in case, like, for example, it's possible to simplify mods and diffs if you know the ranges of the variables. And to address all of these issues, we created indexing map, which is just like an MLIR affine map plus some metadata. And here you can see a simple affine map with one dimension and two symbols. And in the indexing map, we also have additional ranges specified for every dimension and symbol variable, and we have constraints, and also just a flag to indicate whether it was simplified or not. By the way, if you have any questions, just interrupt me. It would be easier to answer them while I'm here. So just to give you an example of dimension variables, let's consider a broadcast of one-dimensional tensor to a three-dimensional tensor. And if you want to compute an indexing map from every element of the output to every element to the elements of the input necessary to compute this element of the output, we will get something like that. So you have D0, D1, D2 that span all dimensions of the tensor, and they map to D1 because only that's the original dimension of the input. We have mappings from output to input of the op, from input to output, and also mappings from GPU grids, like threads and blocks, to tensors, but I will talk about that later. Also, there are range variables. Sometimes if you want to compute one element of the output, you need to iterate over a slice or like several elements of the input, for example, for reductions. If you want to compute one element of this reduction, you need to iterate over 256 elements of the input. That's why we are using symbols for that, just to distinguish between like dimensions, which are just kind of fixed elements of the output, and symbols are just like a placeholders for induction variables that iterate over some reduction dimensions in this case. So we have D0, S0, then map to S0, D0. And yes. So the symbols correspond to range variables, and range variables appear in reductions, in convolution, in reduced window, just max pooling. So like all reduced or contracted dimensions, they will be symbols. Also, we have runtime variables. Sometimes there are operations like dynamic update slice, or gather that depend, indexing of these operations depends on the runtime value of some indices. For example, if you take dynamic slice with a dynamic offset, because like in HLO, all the shapes are static, but the offset of dynamic slice can be dynamic. So we get the following. We get D0 that spans the dimension of the output because it's tensor of 16 elements. And we have S0 that goes from 0 to 47 because those are the feasible values of your offset, because otherwise you get out of bounds. So you can extract 16 elements only if you start at index 0 or like all the way up to 47 elements. And here we also specify the HLO that provides this index. This is needed for different folding that we can perform. For example, if this dynamic index was some function of a constant or iota or some broadcasted element or an add, we can fold it into the indexing map and get rid of the dynamic value. Ranges. Ranges are specified for dimensions and symbols, so like for range variables, for runtime variables, and for dimension variables. And if we take a value outside of this range, then the indexing map is not valid and it should be ignored. For example, for concat, we concatenate 2 by 5 and 2 by 11 tensors, and we get 2 by 16. And the mapping from output to input exists only to one of the outputs at a time. So the value, the mapping to the from output to operand 0 exists only for D0 from 0 to 1 and D1 from 0 to 4. But for D1 from 5 to 15, we have a mapping only to the second operand, so like to operand 1. We can have more complicated constraints. So sometimes we have constraints that have either a dimension and a mod or several dimensions or some combination of symbols, and we can also model them. So for example, here we have a pad for like 4 by 4 elements to 12 by 16, and we have low padding, high padding, and something that I think not many IRs do is the interior padding. It means that we insert elements between the elements of the input. So we can model that using the mod constraints, like D0 minus 1, mod 2 equals 0, pretty much. And outside, like if you look at the padded output outside, or like for indices for which this constraint is not valid, the mapping also is not valid. So we can even code gen this padding by using the indexing map alone, because we know like if the constraints within the indexing map are satisfied, then we populate the element of the input. Otherwise, we just take the neutral element. Indexing maps, just like affine maps, they can be composed and also deduplicated, because if you have a fusion that has many ops inside, and for every of these ops, you have an indexing map from output to input, you can compose all of them and compute an indexing map from the output of the fusion to the input of the fusion. In this case, we have an binary op that takes two transposes, different ones, and then an element-wise op, and then again transposes. And if we follow each of the dev chains, we get different indexing maps, but after simplification, they actually become the same indexing map and they will get deduplicated. So we can use the context information about ranges of the variables and the given constraints to simplify the indexing map. Here you can see a very complicated expression for the reshape. And it's like, this is a combination of two reshapes, I think. And we can simplify, like knowing that D0 and D1 are, knowing the ranges of D0 and D1, we can simplify this expression and just becomes an identity map. Same with runtime variables. Like if we know the instruction that provides a runtime index, we can sometimes simplify it and get rid of it completely. Here you can see the S0 that is computed by doing add of a broadcast and iota. And after folding, S0 just disappears. And we get this nice expression, which is very useful because that means that you can just take a look at some fusion, compute all indexing maps, and sometimes you can analyze and get some compute coalescing or some other useful information. So all of that probably sounded like Linalg generic, because Linalg generic has a similar concept. It has affine maps for inputs and outputs, and the assumption is that every element of the output is populated. That's why Linalg generic can model MapReduce and different Einstein summation and dot, iota, const, whatever, but not everything. For example, reduce window and convolution cannot be completely modeled because it like reduce window can have a dilation or some weird options that require interior padding, and that right now it cannot be modeled by Linalg generic. But we also support other operations like reverse and reshape and concat gather pad. Reverse can be supported by Linalg generic in a static case, but you cannot tile it. That's the limitation. It probably can be lifted. And dynamic update slice, dynamic slice and gather cannot be because only affine maps without symbols are allowed in the Linalg generic. Concat doesn't work because there are no constraints. And same goes for pad. We also use indexing maps to model the mapping from threads and blocks of GPU to roots of the fusion, or sometimes like some other tensors within the fusion. And here you can see a thread mapping for a kernel that just has one element-wise, like unary element-wise op. Like this tensor that produces tensor of 20 by 30, 40 by 300 elements. And in this indexing map, you can see that dimensions are IDs of threads and blocks, and the symbol is a vector element, because sometimes every given thread can read, let's say, 4 elements. If we are talking about F32, we can read 4 elements at the same time. Yes, so that's how we model thread ID mapping. And if we know thread ID to tensor mapping, and we know all the mappings from output to input for the ops within the fusion, and then we also know the layouts of the operands of the fusion, we can actually compute coalescing, like whether the read patterns are coalesced or not, because we can get a map from every thread to the physical, like linearized physical layout of the input. And from there, it's very easy to understand whether the read is coalesced or not. We also have an MLIR attribute for indexing maps. It looks almost exactly as they on the previous slides. We just have this hash XLA GPU indexing map. So it's, again, a affine map with domain information. And we have an op similar to affine apply. In this case, it's XLA GPU apply indexing, which also can evaluate this map. And it becomes useful during code generation, because if you have apply indexing op and you know everything about ranges of the indexing op inside, then you can vectorize the tensor extract. For example, here you can see a tensor extract that computes that like within the loop that goes from 0 to 4, it extracts some elements and that does something with them. But the elements are computed by apply indexing, and we can take a look at this map and we can see that, oh, it just has this plus D2 that depends on the induction variable of the loop. It goes from 0 to 3, and we can use that and the alignment information, and we can vectorize the tensor extract, and it becomes this, like it becomes a vector transfer read hoisted outside of the loop, and then we have vector extract per element, which is quite useful on GPUs, because on GPUs you have just vector loads and stores, but you don't really have vector operations for the compute. Also, we have another layer of abstraction, which is XLA GPU loop. It is equivalent to an SCF loop nest with a inbound check for the constraints of the indexing map. It's useful because we can do peeling. Once you have an XLA GPU loop, you can analyze the indexing map that it iterates over, and if it has some constraints, you can try to adjust the ranges and split the domains into two domains. And the first one can be simplified because sometimes you can just like for the peeling in MLIR. In peeling, you just split the loop into two so that the extract slice gets a perfect tile and doesn't have any dynamic computations for the tile size. Here we do the same, but we just split domain into two domains so that the first one has fewer constraints, which means that in the end, if you have fewer constraints, you don't insert additional ifs, and then you can probably vectorize. Also, in a similar way to Linalg to memref path, I think it's Linalg to loops. I forgot the name of the path. We have a similar logic for elemental emitters. So we have dot, pad, reduce window, and conf that are lowered to loops using the indexing maps. Just instead of assuming that the ranges for the dimensions are given by the output of the Linalg generic, we just take a look at the ranges that are attached to the domain information of the indexing map. Also, indexing maps are used for block level tiling for Triton only right now. And what we do is we symbolically compute tiles, like so offsets, sizes, and strides for every op within the fusion. And then we also compute constraints because, for example, in the fusion, you can have some ugly reshapes that introduces an additional constraint on the tile size. For example, like, oh, tile size has to be divisible by 4 or by 8 or whatever. And then we use it to lower to Triton and also to quickly adjust tile sizes because we have auto-tuners that iterates over a set of different tile sizes and tries to generate code. So in future, like right now, we just support HLO instructions, but in future we will probably support stable HLO or some other MLIR dialect and compute indexing maps for all the ops within the dialect. We will use indexing maps in the cost model and also stop using affine map as a backend for indexing maps because sometimes it's very slow, especially when it comes to replacing dimensions and symbols. The dimensions and symbols will become also more readable if we have metadata about the type of the dimension. For example, oh, this dimension is a thread ID or a block ID or a tile or an offset, then we can print and parse it nicer. And we also can have a debugger for MLIR emitters that, like, given an indexing map, can visualize what parts of the input tensors it reads and writes to. That's it. Questions?
Nice. I mean, I was going to ask actually one where you mentioned like the support for like HLOs. Are all HLOs supported via the indexing maps?
So all HLO that go through XLA GPU emitters. So we had legacy emitters that would go directly from a fusion to LLVM. And now we have a pipeline that goes through Tensor and Arith dialect and gradually lowers it to LLVM. So now we have an MLIR-based code emission, but the way it works, we still have HLO instructions and HLO fusion, and then it gets converted and scalarized at the same time. Soon it will change because we are working also on So right now we have 7 emitters, which is like recipes for different kinds of fusion. Like if you have a reduction, or if you have a transpose, a loop, a scatter, whatever. And we are working on unification of all of that. And we will need some dialect in the MLIR to represent MLIR emitters on tensors. And that's the time when we will probably need indexing maps in MLIR, on MLIR ops. But it will work exactly the same. It will work like, oh, given this op, give me a map from output to input or from input to output. And in this slide, you can see what ops are supported right now. And that covers everything that we needed for emitters, at least. But in XLA GPU, matmols and convolutions, they don't go through emitters. They go through cuDNN or through Triton. So, yeah.
Nice. Well, if nobody else has a question, I'm also curious about the slide where you showed with the being able to fold away the dynamic variable. I didn't quite understand it, but perhaps that is the function. Yeah, it's that one. Right.
Yeah.
Yes.
I can. So usually in the MLIR, you would do that in some pass, right? You would have, let's say, affine apply, and you would have an affine expression, and then some folding would be done just using canonicalization patterns or fold or something. But here we also use indexing maps because we before we are even in the MLIR, when we are just in C++ in HLO. And for example, during priority fusion, when we compute cost model, we can compute coalescing. And to do that, we can sometimes simplify and fold some of the runtime variables. So for example, if you have like eight GPUs and you have a huge HLO module, and it will be split into 8 different ones, and it will introduce a dynamic value of the GPU ID. But you know the range. It's like, oh, it goes from 0 to 7 closed interval, and you can use this information to simplify the indexing maps and potentially improve your analysis. That's why it's needed. But in MLIR emitters, once you are in MLIR, it's not really needed because you have other canonicalization patterns that will fold into apply indexing or XLA GPU loop and simplify everything. Did I answer the question, or did I make it even more confusing?
No, I think you did, but I think I was also perhaps asking a simpler one where, for this specific example, why the like the S0 could be discarded, but that I think you actually explained it. I was not reading it.
There would be an easier example if you have, let's say, dynamic update slice. In XLA, you don't have a static equivalent of that, so you don't have like just update slice without dynamic. Well, dynamic update slice always takes an offset where you insert, but that offset can be just a constant. It can be HLO.constant that produces you this offset. And it would be very nice to just use the constant value instead of just some runtime variable in the indexing map that you compute. That's what it's used for. Because sometimes, like in many cases, you can actually fold this runtime variable away, because you can see that like, oh, it's a broadcast of IOTA. That means that I can use my dimension of the output to compute the index, because IOTA depends on my on the index of the dimension.
Okay, thanks, it helps. Does anybody else have some questions?
I have a quick question.
Mhm.
Hey, Alex. So in the slide where you have the Venn diagram of like Linalg generic as a subset of a superset.
Yeah.
Yes. So what is this like? Do you have an op that is a superset of what you can do with Linalg generic? It was just not clear for me. What is that superset?
So this superset is the ops that we compute the indexing map for. So Linalg generic kind of covers all of the MapReduce-like operations, and we can
Right.
cover a bit more. That's what it means. Because Linalg generic in the end is just a loop. It's a loop nest with indexing maps. So
Right.
when we take a look at XLA, where is it? XLA GPU loop, it's very similar. It uses indexing map, but it's much more flexible.
Right.
Because you can define crazy domains with some weird constraints, and it will still work.
Right. So let me say it, and please correct me if I got this wrong. So the superset is a loop nest where the iteration domain is defined by arbitrarily affine map.
It's an arbitrary affine map, and it's also defined by the constraints. Because like in XLA GPU loop, when you have box constraints for your dimensions and symbols, but
Right.
once you and that's how you iterate.
Hmm.
So this is your iteration space. But when you hit an index combination that doesn't satisfy the constraints, you just continue. So that it will just skip the element.
Right.
So like
Got
for padding, if you have just like, if you increase the sizes of your dimensions, you just want to populate only elements of the smaller subtensor. And you can just model it with XLA GPU loop.
Got it. Cool. Thank you so much. Thanks.
Thank you. Any other questions?
I'm sort of curious, what is required for the stable HLO support? I mean, it seems like you have like most of the mappings you already have for like the indexing maps for your operations. What else is needed to support stable HLO?
So one of the ideas was to unify to unify HLO instruction and stable HLO by using adapters for the ops, and then you can create adapters using the parameters of HLO instruction or stable HLO and just compute the indexing map using that. That's, I think, the most of it. But also, if we are in the MLIR, instead of HLO instruction for the runtime variable, like here, we'll have to use some MLIR instead, which is also like it's easy to unify. We just didn't have need for that yet. But in principle, stable HLO and HLO instructions are almost the same. There might be some slight differences in the options or like attributes of the ops, but that's pretty much it.
Awesome. Yeah, thank you very much for presenting. This is very interesting. I mean, I'm glad to see this is rolling out XLA GPU side. We also have a different project where we've started to poke and prod at using these. And so thus far it's been quite nice. And even with the composition, just actually the amount of fusion that ends up happening due to like the composition of these indexing maps have been actually very nice to see, and produces some reasonably clean like IR output. So I've basically thanks for doing this work.
Also, indexing maps reduced a lot of indexing computations in our kernels because we simplify the indexing map before generating code for that. And that usually leads to much nicer IR.
Awesome. Well, if there's no more questions today, I want to just thank the speaker, and then thanks everybody else for attending. We'll of course upload this again shortly, and then hope to see folks shortly. Oh, and just as a small plug, there will be an MLIR workshop again as part of the LVM Dev meeting. The call for proposals are open, so please feel free to fill in the form and suggest some topics and talks, and also points of discussion that could be had there. All right. Thanks, everybody.
Definitely.
Have a great day.
Bye.